Welcome to Lab 2, the second part of the tape experiment, where instead of looking at the charges as point charges, we considered them as distributed along the entire length of the tape. So the purpose of this lab, as I just said, was to determine the amount of electric charge that causes two strips of tape previously rubbed together to attract to each other, based on in-class experimentation from 2 weeks ago. The calculations this time around were done assuming that the charges are evenly distributed. This is how...
Tell me how you prepared the tapes. I want to know that first. You have to know.
Should we try it?
Go ahead.
Try and see if it works.
You take the tapes and pull it apart.
Yeah.
Okay.
I just hold it over it. Oh, it doesn't work.
So, with that, the procedure that you're not really seeing in the video is that we took two pieces of tape of equal length, assuming that the length, taking equal length will therefore, translate to having equal mass, and we stuck them together, rubbed them very thoroughly, and then pulled them apart very carefully to separate the charges. We tried not to handle them too much. This was discussed in the past lab, but overhandling them means that some of the charges will switch back, and that leads to the experiment not working as well because the charges aren't so evenly separated. Then we lowered one piece of tape down over the other and watched as the charges caused the other one to move up. So some formulas that we use here, we are notably not calculating for our final answer the value of the electric field, which is the second formula on the screen. Instead, we're calculating the force by the electric field, which is relevant because we're setting that force equal to the gravitational force. And basically, a huge part of how this experiment works is making sure that the force vector of the gravity is equal to the magnitude of the force vector for the electric field. The magnitudes have to be equal and the unit vectors have to be opposite. So let's talk about some approximations and idealizations that we used. First of all, we ignored air resistance. Obviously, the force of drag is something that you could consider, but working on such a small scale and with something that is so light, we just did not consider it. The second part, the next 2 points are related to the differences between this first lab and the second one. So in the first lab, we would have said that that second point is relevant, but actually in this lab, we're only saying that the third point is relevant because each tape, we're assuming that it has the same amount of charge evenly distributed along the length of the tape, and we're not treating it as a point charge this time. That's the whole point of the lab. So let's talk about some relevant code here. Basically, the way that this code works is we're finding out our E field first, and we're basically just taking those calculations, creating vectors with them, and basically this Q that we have here, when I first ran through this code, it was the Q that I had found in the first lab, which is a slightly smaller value, but still on the order of 10 to the negative 9, which we'll talk about later. So basically this code has you iterate manually, switching the value of Q, so that in the end, when you're outputting this, the magnitude of the electric field has to be equal to the magnitude of the gravitational force. So you can see that I got pretty close there with 3.3 times 10 to the negative 9 as the Q. So that ended up being our final answer. And you can see in the diagram that the yellow force is the gravitational force vector, which is pointing down, and it's equal and opposite to the electric force vector, which is pointing up. And that is why we're basically taking the two tapes to have been floating in air, essentially, so that the two of them are equal. And I think that pretty much summarizes how the code works. Here, this is pretty straightforward E-field calculations, and then this is just manually doing the work of taking the integral, which is what the procedure that you would do if you're doing it by hand. So yes, our final result ended up being 3.39 times 10 to the negative 9 for our charge. This is ever so slightly larger than the value found in the first lab. You can see the differences there, but they're still on the order of 10 to the negative 9, which I feel means that the point charge model is actually pretty good, if not, it's pretty good for not being super supported in terms of the actual theory of what's going on, like the physicality of what's happening. So let's talk about that. Basically, the difference is that in real life, we can't assume that the point is only in the middle of the tape. So we're gonna assume that the value that we got from this experiment is the more correct value, because in real life, we rubbed those tapes together along their full length. We pulled them apart on their full length, and therefore the charges are distributed along the entire thing. So to limit the calculation to only working with like 2 points is an oversimplification, although it did work on this small scale, giving like a reasonably close estimation. It's obvious from the get-go that that way of doing things wouldn't have worked, because even in the video, you can see that the sides of the tape actually stood up first before the rest of it.
Hold it over it.
Watch that.
Oh, it doesn't work.
So it's clear that there's not only charges distributed in the middle, because you can see it with your own eyes that it's acting throughout the entirety of the tape, and therefore the calculation found in this experiment is a lot more valuable. Thank you for watching.